Hello everyone, myself Sangamesh Jakati, working as Assistant Professor in the Department of Physics, PDIT, Hospital. So from this session, we will start a Module 4, that is Quantum Mechanics and Lasers. And in my various different sessions of Module 4, I'll be covering the concepts which are as prescribed by VTU's 18 scheme syllabus. In this session, our outline of discussion is: first, we'll discuss introduction to quantum mechanics, then wave nature of particles. Afterwards, we will cover Heisenberg's uncertainty principle and its applications. So first, let us discuss introduction to quantum mechanics. Though you are already familiar with most of the disciplines in physics, but I guess you nowhere come across this quantum mechanics. So first let me introduce all of you to this new discipline of physics, that is quantum mechanics. The term quantum mechanics was first coined by Max Born in 1924. But the actual beginning of quantum mechanics date from the work of Max Planck in 1900. However, it was until 1924 that a more complete picture of quantum mechanics emerged and the true importance of quantum mechanics became clearer with the de-Broglie's matter wave hypothesis. The most notable scientists such as Max Planck, Albert Einstein, Niels Bohr, de-Broglie, Max Born, Dirac, Heisenberg, Pauli, Schrödinger, C.V. Raman, Richard Feynman made important contributions to the development of quantum mechanics. Thus, quantum mechanics serves as a foundation for several disciplines of science and technology, like nanotechnology, quantum chemistry, quantum computation, structural biology, condensed matter physics, particle physics, and electronics. So to summarize, quantum mechanics is the study of behavior of matter and energy on the scale of atomic and subatomic dimensions. But classical mechanics is the study of motion of celestial and terrestrial bodies which are moving with the speeds lesser than that of the velocity of light. For example, the motion of a train, bus, car, even aeroplanes, and also the motion of planets and stars, they all comes under the study of classical mechanics. But in the quantum mechanics, it is the transient motion of electrons, the transition of the atom from the higher energy state to lower energy state where the photon gets emitted. So all such a transient phenomena will be studied under this quantum mechanics. With the discovery of electron by J.J. Thomson, exploration of atomic or microscopic systems were started. But it soon became clearer that the classical concepts cannot be applied directly to the motion of electrons in an atom, which are not observable with the help of any instruments, which leads to failures of classical mechanics. Since classical concepts do not hold in the region of atomic dimensions, many difficulties were encountered in explaining the phenomena such as stability of atoms, then spectral distribution of heat radiation in the black bodies, specific heat of solids at low temperature, photoelectric effect, Compton effect, then optic line spectra or called as a atomic spectrum. So it was found that the observed properties of matter cannot be explained on the assumption that particles obeys laws of quantum classical mechanics. This inadequacy of classical mechanics led Max Planck to introduce the new concepts like the emission or absorption of electromagnetic radiations takes place as a discrete quanta, a packet, each of which contain an amount of energy, that is a packet of energy. These concepts led to a new mechanics called quantum mechanics. So nature loves symmetry. We observe most of the things in the nature are highly symmetric. For example, let us consider an onion, that is a vertical cross section of an onion. So here, if I draw a vertical line here, we can see that the left portion of this onion, where the curves and lines, they exactly coincides with the right side portion of this onion. So here the onion is highly symmetric in nature. In the same manner, if you consider leaves, most of the plants in the nature are highly symmetric. So here, if I draw a horizontal line here, the upper portion of these leaves exactly coincides with the lower portion. So leaves are also highly symmetric in nature. And a peacock. So here, if I draw a line, vertical line again here to this peacock, and we can see that the peacock's feather stalk, the left portion of that exactly coincides with the right side portion of the feather stalk. Not only the feather stalk, even the whole peacock itself is highly symmetric in nature. And even our face, the complete whole body, our whole body is highly symmetric in nature. So if you draw a vertical line here, so left side parts coincides with the right side parts here. So these are highly symmetric in nature. Our body is also highly symmetric in nature. So man-made construction, that is, this is a Taj Mahal. So it is highly symmetric in construction. So here again, if you draw a vertical line here, the left side portion of the building exactly matches with the right side portion. And if you fold this Taj Mahal image along this vertical line, exactly the left side portion exactly fits to right side part. So this construction is also an highly symmetric one. So that's why Taj Mahal looks beautiful. So now let us move to the wave nature of particle. Here the particles are behaving like a wave, means particle in general, that is called as a matter. So matters, they are exhibiting wave-like characteristics. Those are called as a matter waves. So first this hypothesis was proposed by de-Broglie. So to understand this de-Broglie's hypothesis, so first we should know what a particle is and what a wave is. So for a particle, the concept of mass is easy to grasp and can be located at some definite point. So it has some fixed point. So if it occupies some space, it is fixed at that point. And a particle is specified by mass, velocity, momentum and energy. But the concept of wave is a bit more difficult than that of a particle. A wave is spread out over a relatively large region of space. It cannot be said to be located just here and there. It is hard to think of mass is being associated with a wave. So we can never measure a mass. So wave is specified by frequency, wavelength, phase and intensity, amplitude. So a radiation is a wave spread out over a space, and also a particle, which is localized at a point in the space. However, this acceptance is essential because radiation sometimes behaves as a wave and other times as a particle. So radiation including visible light, infrared radiation, ultraviolet, X-ray, etc. behaves as waves in experiments such as interference, diffraction, polarization, etc. So the same radiation, when it undergoes a photoelectric effect, Compton effect or Raman effect, is behaving like a particle there. So here in other experiments such as black body radiation spectrum, photoelectric effect, Compton effect, had clearly established the fact that particle is behaving, there is a particle nature of radiation, that is radiation is behaving like a particle. So thus a radiation sometimes behaves as a wave and sometimes as a particle. So in the same sense, de-Broglie proposed a hypothesis based on the symmetry concept. That is, if radiation behaves as a particle under certain circumstances and as a waves under other circumstances, then one can even expect that entities which are ordinarily have as a particle to exhibit properties attributed to only waves under appropriate circumstances, and he termed them as matter waves. So here radiation behaves as a particle. Radiation behaves as a particle under certain circumstances and as a waves under other circumstances. So radiation is behaving like a particle. So in the other sense, in the symmetry sense, in the other sense, so particle is also should exhibit the properties which are attributed to waves only. So here he termed that particle as a matter, and the waves associated with the particle he termed them as matter waves. So if there is a particle, if it is there, so you have to imagine there is a wave associated with that particle. So those waves associated with the particle are called as matter waves. So the wavelength associated with that wave, that is called as de-Broglie wavelength, for any material particle is given by lambda is equal to h by p, but p is equal to mv, that is a momentum. So lambda is equal to h by mv. So if suppose there is an electron which is moving under a potential field v, then the de-Broglie wavelength of that electron is given by h upon square root of 2 MeV. So where h is a Planck's constant, m is the mass of the electron, E is the charge, and V is the voltage that is applied there. So if you simplify this term h divided by square root of 2me, the value that you are going to get is 1.266 nano, that is divided by square root of V. So lambda is equal to 1.266 under root of divided by under root of square root of V nanometer. So you should not confuse this V with the velocity. So this is a applied voltage. Then what are the characteristics of a characteristic properties of a matter waves? Characteristics or properties of a matter waves. So lighter is the particle, greater is the wavelength associated with it. If smaller is the velocity of the particle, so velocity value if it is smaller, then greater will be the wavelength associated with it. The velocity of matter waves depends on the velocity of material particles. So velocity of the matter waves depends on the velocity of material particles. Why? Because waves are associated with this matter. So velocity of the matter waves directly depends on the material particle itself. So it is not a constant. While the velocity of electromagnetic wave is a constant one. As you know, that is the velocity of light, c. The wave and the particle aspects of moving bodies. So if the particle is moving there, then the wave and particle aspects, both the aspects, wave aspect and the particle aspect, so can never be appearing together in the same experiment. So in the same experiment, we cannot have both wave and particle nature. Either we will get wave nature or particle nature. So in the experiment such as diffraction, we only see the wave nature. And in the experiments like the phenomenon like photoelectric effect, where we see only the particle nature. So both of them will simultaneously will not be seen in a same experiment. So this wave nature of matter introduces an uncertainty in the location of the position of a particle, because wave cannot be said exactly at this point or exactly at that point. However, where the wave is large, that is the intensity is large, there is a good chance of finding the particle. While the wave is small, that is a weak, that is the intensity is weak, then there is a very small chance of finding a particle. So where there is a intensity of the wave is more, then there is a more chances of finding a particle. And if there is a intensity of the matter wave is less, then there is a less chances of finding a particle at that position. So now let us move to another important concept in the quantum mechanics, that is called as a Heisenberg's uncertainty principle. It states that it is impossible to specify. Specify means measurement. So it is impossible to measure precisely and simultaneously. So if you make a measurement, that is a precise one, that is a simultaneously. If you measure precise measurement of the values of both number of a particular pair of a physical variables that describe the behavior of atomic system. So there is an atomic system, and in that you are going to measure two pair of a physical variables, a pair of a physical variables, that is a two physical quantities, two variables you are going to measure there, same position and momentum. So if you want to have the measurement of these two variables simultaneously and precisely, then it is not possible. So if you go on finding precise measurement of two physical variables which are related to atomic system is highly impossible. So we can illustrate in the following manner. So consider a particle that is there in the atomic system. So delta x be the error in determining its position, and delta p be the error in determining its momentum during simultaneous determination. So delta x, that's a position and momentum. So during simultaneous determination of both position and momentum, that is the error in the measurement of its position and the error in the measurement of its momentum. So delta x indicates error in the measurement of position, delta p error in the measurement of its momentum. So product of these two errors is at least of the order of h upon 4 pi or greater than that. So here in the same manner, the simultaneous determination of this angular position and momentum is at least of the order of h upon 4 pi or greater than that. Similarly, the simultaneous determination of energy and time is at least of the order of h upon 4 pi or greater than that. So say this is equation 1, 2, 3. So let us consider the first equation, that is a relation 1, which means that a component of momentum of a particle cannot be precisely specified, that is measured, cannot be precisely measured without loss of all the knowledge of corresponding component of its position. So here you are measuring these two. Suppose if you want to measure this one quantity precisely with 100% accuracy, so you need to lose the knowledge of this momentum. And suppose if you want to measure this momentum precisely, you need to lose the knowledge of all the knowledge of this position. So that is the meaning in a particular direction without the loss of all the knowledge of its momentum component in that direction. And in the intermediate cases, suppose if you want to measure this position and momentum simultaneously, so where simultaneous measurement of this momentum and position will be of the order of h upon 4 pi or greater than that. So if you go for measuring simultaneously both position and momentum, so corresponding position momentum components, at least they will be having an error of the order of h upon 4 pi. That's the meaning of this equation 1. In the equation 2, similarly, which means that precise measurement of this angular position. So if we go for measuring 100% precise measurement of its angular position, then which is present in the orbit, carries with it the complete loss of all the knowledge of its angular momentum. And suppose if you want to measure this angular momentum alone precisely with 100% accuracy, that is present in the orbit, so you need to lose all the knowledge of this angular position that is present in the orbit. So similarly, simultaneous measurement of the energy and time, so which is for this we may consider the observation made over a period of time on the energy emitted by an atom, and a simultaneous measurement of this energy and time will be at least of the order of h upon 4 pi or greater than that. So now let us apply Heisenberg's uncertainty principle to this particular case. So we know during radioactivity, 3 kinds of rays that are emitted, that is alpha, beta and gamma. So these 3 kinds of rays are going to be emitted from the nucleus. And since beta rays are actually a stream of electrons, so beta rays are actually containing the stream of electrons, so that the question is it possible that electron exists inside the nucleus with a certain energy? So as you know, in the nucleus there is a presence of only proton and neutron, but there is no presence of electron. But the electron is revolving around the nucleus. But in the nucleus there is no presence of electron. But here beta rays are actually the stream of electrons and they are emitted from the nucleus. So this raises a question that electron must exist inside the nucleus. So by applying this Heisenberg's uncertainty principle, we will disprove the existence of electron inside the nucleus. So theoretically, answer can be given on the basis of Heisenberg's uncertainty principle. So that is impossible for the electron to exist inside the nucleus. So non-confinement of electrons inside the nucleus. So now we will prove that. Non-existence of electrons inside the nucleus. So a typical value, let us consider a typical value of the diameter of the nucleus, which is of the order of 2 into 10 raised to minus 14 meter. If the electrons were to be present inside the nucleus, suppose if the electrons are there inside the nucleus, the maximum uncertainty, that's a delta x. So delta x is the uncertainty. We are allowing the maximum error to happen. So maximum uncertainty delta x in the measurement of its position is equal to the diameter of the nucleus. So this itself is the diameter. So if you want to measure the error in the measurement of its position inside the nucleus, so I am taking, the error in the measurement of its position is maximum. So in that case, the maximum error that happens is 2 into 10 raised to minus 14 meter, and that delta x will not exceed this much of value. So I am allowing this much of error to happen. Suppose if you take a scale, the least measurement, the least error you can make in that centimeter scale is 0.1 centimeter. So maximum error that you can make while making a measurement is 15 centimeter. So if you take a 15 centimeter scale, the maximum error that you can do is 15 centimeter. So it will not exceed that much of value up beyond say 15 centimeter. So our region of space is only 2 into 10 raised to minus 14 meter. So the maximum uncertainty, maximum error that can happen while measuring the position is 2 into 10 raised to minus 14 meter. So according to Heisenberg's uncertainty principle, delta x into delta px, so px indicates the momentum that is done along x direction. So simply it is a position and momentum. So delta x, delta px, which is greater than or is equal to h upon 4 pi. So I am keeping this delta px to LHS and bring this remaining this delta x to RHS. So this becomes 1 over delta x. Say this is equation 1. So here h being a Planck's constant, 4 pi is a constant, and delta x we know the value, how much it is, 2 into 10 raised to minus 14 second. So here delta px is the minimum uncertainty in its momentum. So delta px becomes, after substituting all the values, constant values, so here we got the simplification 5.2 into 10 raised to minus 21. That is kg meter per second. Say this is equation 2. Thus, the minimum energy of the electron in the nucleus is given by E is equal to mc square. So E minimum is equal to mc square. This is Einstein's mass energy relation. So here in the place of m, I will replace this m with p by c. So how it is? Because we know momentum p is equal to mv. So instead of this v velocity, if I replace with the velocity of light c, so it is same, p is equal to mc, p is equal to mv, it is mc also, it is mv. So here p is equal to mv, I'll keep this m one side and bring remaining terms to other side, that is the LHS. So m becomes equal to p by c. So here it is p by c, so px by c. So c cancels here, simplification becomes px into c. So the minimum uncertainty in the momentum can be taken as the momentum of the electron. Thus, E minimum becomes 5.22. So we are substituting that found already determined value, and c value, that is a constant velocity of light, that we are substituting here. So after substitution, the simplification becomes 15.6 into 10 raised to minus 13 joules. And if I convert this joules into electron volt by dividing it by 1.6 into 10 raised to minus 19, we will get 15.6 10 raised to minus 19, this is joules, and in electron volt this is 9.75 into 10 raised to 6 electron volt, and that value 9.75 can be approximated to 10, and 10 raised to 6 is a mega. So this is 10 mega electron volt. So E minimum is 10 mega electron volt. So this means to say that in order that an electron may exist inside the nucleus, its energy must be equal to 10 mega electron volt. But the experimental investigations on beta decay reveal that the kinetic energy of the beta particle is of the order of 3 to 4 mega electron volt. So this clearly indicates electron cannot exist within the nucleus. So this is the hence we disproved the existence of electron inside the nucleus. So in this session we discussed introduction to quantum mechanics first, then afterwards we discussed wave nature of particles, afterwards we discussed Heisenberg's uncertainty principle and its application. Thank you.